All right, so now we're going to start Module 2 for Chapter 11. And Module 2 for Chapter 11 goes in your notebook on page 153 to 155. And these are the theorems. There's a lot of different theorems in this chapter. And when we go through them today, they might be a little bit confusing. But in the next modules, Module 3, 4, 5, and 6, you're going to see how to apply them. And hopefully they'll make more sense. Now, you needed the pages to glue in, so that the theorems are already written down for you, and then you just need to add in the diagrams and to help you understand these theorems, okay? So we're gonna start with page 153, and at the top, these are talking about theorems that have to do with arcs and chords. So the first theorem says, in a circle or in congruent circles, two minor arcs are congruent if and only if their corresponding chords are congruent. So if you look here, we have minor arc WX, and we also have minor arc YZ. And if you notice, the segment connecting them is 11 units long for both. So since 11 is the same as 11, we can also say that these arcs are congruent. So that's why they wrote that arc WX is congruent to arc YZ, because their measures are congruent. So both the part that's curved, the arc, is congruent in both of these, and the segments are congruent. So it works either way. If your segments are congruent, then your arcs are congruent. If your arcs are congruent, then your segments are congruent. Then the next one, it says, if in a circle, if a diameter is perpendicular to the chord, then it bisects the chord and its arc. And remember that bisect means to cut in half, and it's two perfect halves. So if I have a diameter, and everyone can see here that this is a diameter, okay, it goes through the center of the circle, touches both sides. If I have a diameter and it's perpendicular, that's that right angle right there, that means that it bisects AC. So however much it is to get from A to D, it's the same amount to get from D to C. It's bisecting that. The next theorem says, in a circle or in congruent circles, two chords are congruent if and only if they are equidistant from the center. So here they told me that from WX, arc WX, and here arc ZY, it says that they're congruent. Well, the reason why I know that they're congruent is because these are both 5 units from the center. Do you see they're both the same amount? Because they're both the same distance from the center, that means that arc WX and arc ZY or YZ, they're congruent. But also it means that the straight line that connects WX is also congruent to the straight line that connects Z and Y. So both of those are congruent. So the curve, the arc here is congruent, and the straight line is congruent because they're the exact same distance from the center of the circle. Okay, these are continuing on page 153. And so these are talking about inscribed angles. Okay, so this is an inscribed angle because its vertex is on the circle and its sides of the angle are chords to the circle. It says if an angle is inscribed in a circle, then the measure of the angle equals 1/2 the measure of its intercepted arc. So if this has a degree measure, whatever it is, this is half of it. So if arc X was, let's say 90 degrees, then that means that this angle would be 45 because that's half of it, okay? If arc X was maybe 70 degrees, then that means that angle would be 35 degrees because it's just half, okay? Then if you notice here, I have 2 angles. I have this angle here, and then I have this angle here. But do you see how they have the same intersected arc? So it says if 2 inscribed angles of a circle or congruent circles intercept congruent arcs or the same arc, then the angles are congruent. Because they both have the same points of intersection, whatever this angle is going to be the same as that angle. And it makes sense because if you think about it, they both go to the same arc. Then it says if an inscribed angle of a circle intersects a semicircle. So that means half, right? Semicircle. Then the angle is a right angle. So if this is a diameter, then I know this angle has to be 90 degrees every time. And then this arc we know is 180 degrees because it's half of a circle. And then the next one, it says if a quadrilateral is inscribed in a circle. And when I use the word inscribed here, that means all 4 points have to be on the circle. Okay, an inscribed quadrilateral couldn't look like this. This is not inscribed. Even though it has 4 sides, this vertex here is not on the circle, so that is not inscribed. So if a quadrilateral is inscribed in a circle, then its opposite angles are supplementary. So A and C are supplementary, and B and D are supplementary. Now we have the theorems that go on page 154. Okay, so make sure you have that page to glue in and that you're drawing these pictures in the circle onto your circle so you have them. It says here, if a line is tangent to a circle, then it's perpendicular to the radius drawn to the point of tangency. So this line is tangent to the circle. That means it intersects in one place. And they're saying if I go from that point of tangency back to the center, it's a radius and it's always going to be perpendicular every time. And then the next one says if in a plane, if a line is perpendicular to the radius of a circle at the endpoint of a circle, then the line is tangent. So this one says if the line is tangent, then I know it's going to be a right angle. And here it says if it is a right angle, then I know this line is tangent. So this is what we would call, when we go back and forth, this is the converse of each other. So it's like it works both ways, we could say. If we have a tangent line, then we know it's a perpendicular. If we have a perpendicular, we know the line's tangent. Okay? And then the next one says, if 2 segments from the same exterior point are tangent to the circle, then they are congruent. So do you see A and C, how this line intersects the circle in one spot and this line intersects the circle in one spot? So both of these lines are tangent, which means from B to A and from B to C is the same amount. So AB equals CB because they are both tangent to the circle. All right, we have 3 more theorems for this page. If a secant and a tangent intersect at the point of tangency, then the measure of each angle formed is 1/2 the measure of its intersected arc. So here we have this angle, and what they're saying is this angle here, its measure is half whatever this arc is. So let's just say this arc is 80 degrees. That means angle BCA is going to be half of 80, which would be 40 degrees. Now we know a whole circle from here to here. The whole circle, though, is 360. So from there to there would be whatever 360 minus 80 is. Okay, so when we do the subtraction problem, we see that this arc here is 280 degrees, which means this angle of C, which doesn't have a name, but so we'll just call it angle C because there are 3 points to call that one, would be then half of this, which is 140. Now notice that these two have to be supplementary because they make a straight line, but that's what that theorem means. The next one says if 2 secants intersect in the interior of a circle, then the measure of the angle formed is 1/2 the sum of the measures of the arcs intercepted by the angle and its vertical angle. So what they're saying here is that angle 1, which is right here, is going to be half the average of arc AD and BC. So whatever this measure is, let's just say that this is 80 degrees and this is 60 degrees. I would say that 80 plus 60 is 140. 140 divided by 2 is 70, which means that this angle here, angle 1, would be 70 degrees. And we know that also means then that this angle over here would also have to be 70 degrees because they are vertical angles and vertical angles are congruent. Now with the next one, there's 3 different pictures, but they all say the same thing. If 2 secant, so that's this picture, if 2 secants, then the next thing it says is a secant and a tangent, so that's this picture here. And then the final one, it says are 2 tangents, that's this picture here, intersect in the exterior of a circle, then the measure of the angle formed is 1/2 the positive difference of the measures of the intersected arcs. And this may be a little bit confusing right now, but basically they're saying that you find the difference between the big arc and the little arc, the big arc and the little arc, or the big arc and the little arc. You find the difference, so you subtract them, big minus little, and then you divide it by 2, and that's going to give you that angle measure. So we'll talk more about that when we get to the section that goes over this. All right, and then our last page of theorems, so this is page 155. It says if 2 chords intersect in a circle, then the product of the measures of the segments of the chords are equal. So this means multiply products. Okay, and so what they're saying here is whatever this is, A, B, C, D, that I can go A times B, and it's going to equal C times D. So one piece times one piece equals the other piece times the other piece. Like I said, we'll go over these when we get to that section. The next one says if 2 secant segments are drawn to a circle from an exterior point, then the product, multiply, of the measures of one secant segment and its external segment is equal to the products of the 2 measures of the other secant segments and its external segments. So sometimes we like to say it this way: outside times whole equals outside times whole. Okay, so this is the outside here, and then this would be the whole line. This would be the outside here, and this would be the whole line. And we'll go more into this theorem as we progress in the chapter. The next one says if a tangent and a secant tangent are drawn from an exterior point, then the square of the measures of the tangent segment is equal to the product of the measures of the secant segment and its external secant segment. So once again, this part is still outside times whole, but here if you notice the outside and the whole are the same number. So that's why they use the word square here, because it's the same value. Even though it's still outside times whole, my outside for this line segment is the same as the whole line segment, because remember, a tangent doesn't go inside the circle. And then the last ones, inscribed angles and intersected arcs. So we talked about this is an inscribed angle. It's inscribed because its vertex is on the circle and its sides contain chords of the circle. Then an intercepted arc. So this is the intercepted arc, and it's an arc on a circle created by endpoints of an inscribed angle. So this is the inscribed angle, and that is its intercepted arc. Okay. Then a central angle. A central angle is an angle whose vertex is at the center. So it's just an angle whose vertex is the center. Like if I'm slicing a pizza correctly, I should be making central angles. And then remember that all the angles, so this whole sum should always be 360 degrees. We know a whole circle is 360, so all the central angles should be 360. Then we have a minor arc, and the measure of this minor arc is 82 degrees. Then the major arc would be the big number, so we would do 360 minus 82. So we need to do this problem here. So we get 8, 7, 278. So if the minor arc is 82, then the major arc is 278 degrees. And then a semicircle we know is half. So semicircle 180 degrees. So these are the theorems for Module 2 for Chapter 11. Make sure you have all the pictures drawn in your book. If you need to rewind it, do so.